Okay, let's kick things off with a big picture view. Generative AI isn't just about making things better, it's about creating completely new things. Think of it as teaching a computer to be creative, to understand the rules and patterns within data, so it can then generate its own versions. It's a pretty radical shift from traditional AI that mostly focuses on recognizing what's already there. Okay, let's rewind a bit and look at how AI has evolved. It wasn't always the sophisticated stuff we see today. In the 50s and 60s, early AI relied on hard-coded rules, basically telling computers exactly what to do. Then machine learning came along, letting computers learn from data instead of being explicitly programmed. Deep learning, using complex neural networks, exploded in the 2010s, powering things like image recognition. RNN and LSTMs were a big step forward for working with text, but transformers really changed the game. They are what make today's large language models possible. Okay, so let's talk about discriminative versus generative models. Discriminative models are like detectives. They're really good at figuring out what something is given some clues. They learn to predict a label directly, like classifying an image as a cat or a dog. Generative models, on the other hand, are more like artists. They try to understand how things are created in the first place, and then use that understanding to generate new, similar data. Think creating realistic images or writing original text. Okay, let's dive into the different kinds of generative models out there. First up are variational autoencoders. They learn a secret code representing data and then use it to create new variations. Then we have generative adversarial networks, which pit two networks against each other, one creating content and another trying to tell what's real versus fake. And finally, we have transformers. These powerful models, like GPT, are really taking the world of generative AI by storm due to their amazing ability to understand context within data sequences. It's important to remember that each type has its own strengths and weaknesses, so understanding them will help you make better choices when working with these technologies. Okay, let's talk about autoregressive models. They're the engine driving almost all modern LLM. Essentially, these models work by predicting the next word in a sequence, one token at a time. It's like playing a really complex game of fill in the blank. They process text step by step, calculating probabilities for each possible word, and then sampling from that probability distribution to create coherent output. They are incredibly good at understanding context and generating text because they're designed to do exactly this: predict what's most likely to come next based on everything they've learned. Okay, let's talk about variational autoencoders, often shortened to VAE. They're a really cool tool for working with large language models and boosting how well they generate text. Basically, VAE are generative models, meaning they can create new data that resembles the data they were trained on. They learn a compressed version of the data, like encoding it into a smaller space. Imagine taking a picture and squeezing all the important details into a tiny thumbnail. That's kind of what a VAE does for text or any other data. It has an encoder which takes your original input and compresses it into this lower dimensional latent space, represented by a probability distribution. Then there's a decoder that tries to reconstruct the original from a sample pulled from this latent distribution. Using VAE in conjunction with LLM allows you to improve generation quality, make text generation more controllable, like steering the style or topic, and even spot unusual inputs. Okay, let's talk about GAN. They're a really cool approach in generative AI. Think of it like an art forgery contest. You have two networks, a generator that's trying to create convincing fake artwork, and a discriminator that's acting as the art expert trying to spot which pieces are real and which are fakes. These two networks constantly battle each other, improving their skills until the generator can produce incredibly realistic data. It's all about adversarial training, a constant competition between these two models. Okay, let's dive into diffusion models. They are a really clever technique behind some of the most impressive generative AI we're seeing today, especially with image creation. Basically, these models start by systematically adding noise to an image until it becomes pure randomness. Then, they train a neural network to learn how to and do that process to progressively remove the noise and reconstruct a coherent image. It's like taking a beautiful painting and slowly blurring it out, then teaching a computer how to repaint it back. The key thing is that they're remarkably stable to train compared to older methods, which means we get consistently high quality results and have much more control over what gets generated. Okay, let's talk about flow-based generative models. Think of them as a really smart assembly line for creating content. Instead of processing an entire thing at once like traditional transformers do, they break it down into smaller, sequential step stages or nodes. Each stage takes the previous result and transforms it, building on what came before. These stages are connected in a flow network, kind of like a directed graph showing the order things happen. A really cool difference is that flows often work with a continuous latent space instead of discrete tokens, which makes generation smoother and gives us more control over the final output. Okay, let's shift gears and dive into energy-based models. Think of them as a way to really fine-tune how large language models generate text. Instead of just predicting the next word, an EBN learns what makes a good sentence. It assigns an energy score to each possible sequence. The lower the energy, the more likely this sequence is considered good by the model. It then samples from this energy distribution, basically picking out the most coherent and fluent options. This helps LLM generate text that's not just grammatically correct, but also flows really well and stays on topic. We can even shape the style of the output, making it more formal or informal, for example. It's a clever technique that gives us a lot of control over what the model produces. Okay, let's start with the basics. We're going to lay some mathematical groundwork for understanding how generative AI and large language models actually work. The first thing we need to get comfortable with is linear algebra. It's like the language of data. Think about representing words as vectors. Linear algebra helps us do that efficiently. Then we dive into calculus, specifically gradient descent, which is basically how we teach our models to learn and improve. Finally, we wrap things up with probability and statistics. Because at its core, generating text or anything really is all about predicting the next likely thing based on what's already been generated. So these three areas are absolutely fundamental. Okay, let's talk about why linear algebra is so important when we're diving into generative AI. It might seem like a bit of an abstract topic, but trust me, it pays off. At its core, linear algebra provides the tools to represent and manipulate data. Think of vectors as individual pieces of information and matrices as ways to transform those pieces. We'll be using dot products, asterisk, lot, asterisk, and attention mechanisms, which are key to how transformers work. And matrix multiplication? That's literally what makes the layers in these models function. Understanding dimensions is absolutely critical here. Finally, concepts like eigenvalues and eigenvectors help us streamline our models and make them more efficient. Let's talk about how probability is absolutely central to how generative AI models work, specifically transformers and LLM. These models aren't just guessing, they're learning the asterisk likelihood asterisk of different sequences, whether it's words in a sentence or pixels in an image. They use something called log probabilities to handle these calculations efficiently. The training process is all about maximizing how likely the model thinks our training data actually is, using a technique called maximum likelihood estimation. And finally, when we want the model to asterisk generate asterisk something new, it's not just picking one thing. There are different strategies for sampling from the probability distribution that the model has learned, like choosing the most probable next word, but with some added randomness, or by only considering a limited set of options. Okay, so let's dive into information theory. It sounds complicated, but it's actually really fundamental to understanding how large language models work. Information theory, developed by Shannon, is all about quantifying information and how efficiently we can send it. A key concept within this framework is entropy. Entropy measures the uncertainty associated with a random event, or in our case, predicting the next word in a sequence. The higher the entropy, meaning more randomness, the less certain we are about what will happen next. We calculate it using a formula that considers the probability of each possible outcome. In LLMs, this entropy is used to determine how likely a particular sentence is. Lower entropy equals higher likelihood. It's really all about how well the model predicts what comes next. Okay, let's talk about getting generative AI models, especially those massive LLM, running smoothly and efficiently. We're diving into optimization in machine learning, and it's absolutely vital. Think of it this way: these models are huge, consuming a ton of resources. So we need to make them leaner and faster. There are several key techniques we can use, things like quantization, where we reduce the precision of the numbers the model uses, making it smaller and quicker. Pruning is another one. Essentially, we're identifying and cutting away unnecessary parts of the network. And then there's knowledge distillation, which is about training a smaller model to learn from a bigger, more complex one. Finally, don't forget about hardware. Using powerful tools like GPU and TPU can make a massive difference. But remember, optimization isn't just about shrinking things down, it's also about understanding the balance between size, speed, and accuracy. You always want to find the sweet spot for your specific application. Okay, let's talk about gradient descent. It's absolutely crucial for understanding how LLM learn. Think of it like this: we have a big problem to solve, represented by a bumpy landscape called the loss function. Gradient descent is essentially rolling a ball down that hill, guiding our model towards the lowest point where the errors are minimized. We start with some initial guesses for the model's parameters and then repeatedly adjust them based on the direction of steepest descent. There are different versions of this process, like using the whole dataset at once, batch gradient descent, going one data point at a time, stochastic gradient descent, or using small groups of data points, mini batch gradient descent, each offering a slightly different balance between speed and accuracy. Okay, let's talk about how we tell these generative models what to learn. It all starts with loss functions. Essentially, they're the model's guide on how well it's doing. Unlike a regular classifier that just says this is a cat, a generative model tries to actually create something new that looks similar to what it's seen before. Because it's creating, we need a way to measure its success. Common ones include measuring the difference between an original piece of data and the model's attempt to recreate it using MSE, or mean squared error. Then there's cross-entropy loss, which is popular in language models for gauging how well predictions match what's actually written. And VAE often use KL divergence to keep things balanced. The specific loss function you pick really shapes the type of output your model will generate. It's a crucial design choice. Okay, let's talk about backpropagation, because understanding this is key to how LLM actually learn. Imagine you're teaching a student to solve math problems. First, they try their answer, that's the forward pass. Then, we tell them if it's right or wrong and calculate the error. Backpropagation is like tracing the steps back through the problem to figure out exactly which parts of their reasoning were off. It finds how much each step contributed to getting the wrong answer. Finally, based on that information, we gently nudge the steps in the right direction, adjusting the weights within the model until the student gets it consistently correct. Okay, let's start with the basics: neural networks. Imagine your brain, but super simplified. Neural networks are made of interconnected nodes called neurons arranged in layers. The first layer takes in the initial data like an image or a sentence. Then there are hidden layers where the magic happens, extracting all sorts of useful features. Finally, the output layer gives you the answer. Each connection between these neurons has a weight that tells it how important it is, and there's also a bias. The network learns by adjusting those weights and biases to get better at what it's doing, minimizing errors and improving accuracy. Okay, let's talk about something super important: activation functions. Think of them as the spark plugs inside your LLM. They allow it to learn complex patterns. Without them, a neural network would just be a straight line. We have different types like ReLU, which is simple and fast, but can sometimes cause problems with training. Sigmoid and Tan are also options, but can struggle with vanishing gradients. SHALU has become really popular lately because it's smoother and often leads to better results. The activation function you pick can dramatically change how your model learns and performs. Okay, let's talk about overfitting, a really important concept when working with LLM. Think of it like this: your model becomes *2* good at remembering the training examples instead of actually learning how to generalize. It's like cramming for an exam and only knowing the specific questions from the practice tests. This leads to great results on things it's seen before, but when you give it something new, it completely falls apart. It happens because we often have very complex models with lots of parameters, train them for too long, or don't use enough data in the first place. The good news is there are ways to fix this. Regularization is a set of techniques that try to prevent overfitting by penalizing overly complicated models. Loan and L2 regularization are two common approaches. Loan encourages some weights to become zero, which can simplify the model, while L2 shrinks all the weights towards zero. Finding the right amount of regularization strength, that's how much you penalize complexity, is key to getting a good balance between accuracy and generalization. Okay, let's dive into two key techniques that help us train really powerful large language models: dropout and batch normalization. Dropout is like a little surprise. During training, it randomly turns off some neurons in the network. This forces those remaining neurons to learn more robust features and prevents them from relying too heavily on any single neuron, which leads to better generalization when we deploy the model. Batch normalization, on the other hand, works by normalizing the activations within each mini batch of data. It essentially makes sure that the inputs to each layer have a consistent scale. This dramatically stabilizes training and speeds up how quickly our models learn. It's like giving them a smoother path to success. Let's talk about RNN. They're really important in understanding how language models work. Think of them as networks with a memory, which is key to processing sequences like sentences. Unlike regular neural nets that just look at one thing at a time, RNN remember what happened earlier in the sequence. They use something called a hidden state to keep track of all that past information, updating it step by step as they read through the data. It's kind of like how you understand a sentence. You need to remember the context of previous words to get the full meaning. We'll break down exactly what each part of this process is and how it works together. Okay, let's talk about LLMs and GRU. These are special types of recurrent neural networks that are super important for how large language models understand and process text. Traditional RNNs struggled with remembering things from the very beginning of a long sentence, but LSTMs and GRU solve this problem with gates. LSTMs have 3 gates: an input gate, a forget gate, and an output gate, giving them really fine-grained control over what they remember and don't. GRU are like a simplified version of the LSTM. They combine some of those gates to be a bit more efficient. Basically, they both have internal memory cells that allow them to retain important information as they read through a sequence of words. Okay, so let's talk about a key problem with older models called RNN recurrent neural networks. They are really good at things like understanding sequences, like sentences or music notes. However, they have a serious issue when it comes to remembering things from *** back in the sequence. Basically, as information passes through an RNN over many steps, it gets weaker and weaker. This is called the vanishing gradient problem. It's like trying to whisper a secret across a crowded room. By the time it reaches the end, it's barely audible. Because of this, RNN primarily have short-term memory, meaning they struggle to truly understand context over really long stretches of text or data. That's why we moved on to more advanced models like transformers, which use attention to directly connect to any part of the input, solving that long-term memory problem. Okay, let's jump into transformers. They're really the brains behind many of today's amazing AI models. Basically, transformers are a totally new way of building neural networks for understanding and generating text. They ditch the old sequential approach, which could struggle with long sentences or paragraphs. Instead, they use something called self-attention, which lets each word in the sentence consider **all the other words at once to understand its context. This allows them to process information much more quickly and effectively. It's like reading an entire book in one go. And because of this parallel processing capability, training these models is significantly faster than previous methods. Okay, let's dive into self-attention. It's honestly one of the coolest parts of how these massive language models work. Basically, unlike older methods that read text step by step, self-attention lets each word look at every other word in the sentence to figure out what's important. It generates 3 things for each word: a query, a key, and a value. Think of it like searching. The query is your question, the keys are potential answers, and the values are the actual information those answers contain. The model then figures out how well each key matches your query, assigns them weights based on that match, and uses those weighted values to build a new, richer representation of the word. It's like highlighting the most relevant bits of context for each individual word. Okay, let's dive into multi-head attention, a really crucial component of transformers and LLM. Basically, instead of just looking at one aspect of the input when trying to understand its meaning, we use several attention heads. Each head is like a mini expert, focusing on different relationships between words or phrases within the text. So, one head might focus on grammatical connections, another on semantic similarity, and so on. They all work in parallel, giving the model a much richer understanding of the context. Okay, let's talk about a really clever trick used in transformers positional encoding. Because transformers don't naturally process words in order like RNN do, we need a way to tell them where each word is located in the sentence. Positional encoding does just that. It adds information about position to the word embeddings asterisk before asterisk they go into the transformer layers. Basically, it uses sine and cosine functions at different frequencies. Lower frequencies capture longer distances between words, while higher frequencies represent shorter gaps. It's a brilliant way to give transformers an understanding of sequence order. Okay, let's talk about how these huge language models actually understand what we're saying. It all starts with the encoder-decoder transformer architecture, really clever design. The encoder takes your initial input, like a question or a piece of text, and turns it into a super compressed numerical version that captures its meaning. This happens through layers of self-attention. Basically, each word is paying attention to every other word in the sequence, figuring out how they relate to one another. Then, the decoder uses this encoded representation to generate the output like an answer or the next part of a story. It's also using self-attention, but this time it's looking at both what is already generated and the encoder's summary to make sure things stay consistent and relevant. And just for good measure, there are some helpful techniques built in layer normalization and residual connections that help keep everything running smoothly during training. Okay, let's talk about two really important types of attention inside transformers. First up is masked attention. Think of it as a model that's trying to guess the missing word in a sentence. It can't look ahead at what comes next during training, so it only pays attention to the words asterisk before asterisk, the blank space. Then we have causal attention, and this is where things get really interesting for LLM. Causal attention looks back at all the previous words in a sequence to help predict the next word. It's like the model is building its response step by step, always referencing what's already been said. Essentially, mass focuses on understanding, while causal focuses on generating text. Okay, so let's talk about feed-forward layers in transformers. They are kind of like a secret ingredient. They sit between the attention mechanisms and are responsible for taking all that focused information and really digging into it. It's basically a small, powerful neural network that processes the data further. It has two main parts. First, it squashes down the information with one linear layer, then boosts it back up again using another, and importantly, uses a ReLU activation function to add some nonlinearity. Okay, let's talk about how these massive language models actually get their skills. It all starts with pre-training. Imagine teaching a child everything there is to know about the world just by letting them read tons of books and articles. That's essentially what we do here. We feed the model an enormous amount of text data, and it learns basic patterns of language. It's like building a really strong foundation. Then comes fine-tuning, which is where we take the already knowledgeable model and teach it to excel at specific tasks, whether it's answering questions, writing summaries, or even generating code. It's all about adapting that general knowledge to do something useful. Let's talk about what these huge language models are actually trying to do. Basically, they're incredibly good at predicting the next word in a sentence. It's like a really advanced autocomplete. They've also learned how words relate to each other and build context within text. And crucially, they can string together words to create full paragraphs and even longer pieces of writing. All this is driven by them learning from massive amounts of data. Think of it as reading the entire internet. Okay, let's talk about masked language modeling, or MLM. It's one of the foundational techniques behind how large language models, like transformers, actually learn to understand language. Think of it like a fill-in-the-blank exercise, but for massive amounts of text. The model is given sentences with words deliberately hidden, and its job is to guess what those missing words are based on everything else in the sentence. It's a really clever way of teaching the model about context, how words relate to each other, both before and after them. For instance, if we have the cat sat on the, it has to figure out that math is the most likely answer. MLM provides this essential bidirectional understanding that makes these models so powerful at generating text. Okay, let's talk about causal language modeling. It's a really crucial concept when we're looking at how LLM actually work. Basically, these models are trained to guess what word comes next in a sentence. They do this by repeatedly looking back at all the words that have already appeared and predicting the most likely subsequent word based on those past words. It's like an incredibly advanced autocomplete function. It's important to remember that they only use information from asterisk before asterisk, no remembering what came earlier in the text. Now, we'll move on to exploring attention mechanisms which build upon this foundation. Okay, let's talk about next sentence prediction, or NSP. It's a really interesting piece of how BERT, and later transformers in general, learn to understand text. Basically, you give the model two sentences, often consecutive ones, from a larger document, and it has to predict whether the second sentence logically follows the first. It's not just about recognizing words, it's about understanding if those sentences make sense together as part of a bigger picture. While its initial impact was huge, research later showed that NSP wasn't quite as vital as originally thought, but it definitely shaped how transformers learned to connect and interpret text. Okay, let's talk about permuted language modeling. It's a clever trick that really helps transformers understand longer pieces of text. Traditionally, language models process words one after the other, which can make it tricky to remember things from way back in the sentence. PLM solves this by completely rearranging the input sequence first. It breaks down the sentence into smaller chunks and then orders those chunks based on how they relate to each other. This forces the model to look at distant relationships directly, leading to a much better grasp of context and improved performance on complex tasks. Okay, so before an LLM can actually do anything with text, it needs a way to understand it. That's where tokenization comes in. Basically, we're taking that big chunk of words and turning them into smaller pieces, tokens. These tokens are just numbers, which the model then uses as its foundation for understanding meaning. There are several techniques like word piece, BPE, and sentence piece, each with slightly different approaches to breaking down text. The type of tokenizer really impacts how well a model performs, so it's an important consideration. Okay, let's dive into byte-pair encoding, or BPE. Think of it as a clever trick that helps large language models actually understand text. Basically, when an LLM is trained, it can't directly work with words themselves. Instead, the training data, huge amounts of text, gets broken down into smaller units called tokens. BPE is the method used to create these tokens. It starts by counting how often pairs of characters or even parts of words appear together frequently. The most common pairings get combined into a single token. This process repeats until we have a manageable vocabulary size. Because it reduces the amount of information an LLM has to deal with, BPE makes training and running these massive models much more practical. Okay, let's talk about how large language models actually understand text. It all starts with tokenization, breaking down words into smaller pieces. Two popular methods are word piece and sentence piece. Think of them as specialized tools for chopping up words. Word piece is a data-driven approach. It looks at how frequently different character sequences appear in the training data, and then builds a vocabulary by combining those most common sequences. It's like learning what parts of words are important. Sentence piece takes a slightly different route. It uses something called a unigram language model. Basically, it treats the whole text as a sequence of characters and learns probabilities for where to split each word. It's more flexible when dealing with new or unusual words. The key difference is that WordPeace tends to be better at recognizing traditional word boundaries, while SentencePiece handles out-of-vocabulary words much more gracefully by splitting them into smaller pieces it's seen before. Okay, let's talk about how LLM actually understand languages. Starts with building a really good vocabulary. Think of it like teaching a child. You need to introduce them to the words they'll be using. LLM do this through something called tokenization, which is basically breaking down text into smaller pieces. There are different ways to do this, and each method has its strengths and weaknesses. We're talking about things like WordPeace and byte pair encoding. Don't worry if those names sound complicated. The important thing is that LLM use these tokens as the building blocks for understanding what you type. A huge factor here is vocabulary size. A larger vocabulary means more options, but it also requires more memory. And, of course, there are special tokens like beginning and end markers to help the model know when to start and stop processing your input. Okay, let's talk about how we actually get the data into these massive language models. It's not just throwing everything at them that won't work. First, we need to gather our materials. Think of it like a huge library, pulling in text from the web, public datasets, and even licensed sources. Then comes the really important part, cleaning up all those messy bits. We're talking about removing duplicates, fixing errors, and making sure everything is consistent. Next, we need to convert that text into something the model can understand, a process called tokenization. Finally, we might augment our data by creating similar examples or translations to help the model learn even better. And because these models are huge, we have to break up the data and distribute it across many computers for faster training. Data privacy, bias reduction, and consistency are also very important things to keep in mind. Okay, let's talk about getting your data ready for an LLM. Think of it like cleaning up a messy room before you start building. A huge part of this process is removing duplicates and filtering out anything that isn't useful. Why? Well, if your training data has the same information repeated over and over, your model will learn those redundancies and might produce biased or less accurate results. There are a few different ways to do this. You can use exact matching, just looking for identical strings, which is quick but not always effective. Fuzzy matching uses techniques like Levenshtein distance to account for typos and slight variations in wording. And finally, for really powerful filtering, you can use semantic similarity models that compare the meaning of text instead of just the words themselves. Okay, let's talk about how LLM gets so smart. It all comes down to scaling. Think of it like this: the bigger you build the model, more parameters, the more data you feed it, and the more computing power you throw at training, the better it generally performs. There are some really clear patterns we've observed called scaling laws. Basically, as you increase the size of the model, the number of connections in its brain accuracy tends to go up. Similarly, feeding it more data also helps a lot. And finally, having access to more computing power makes training faster and results better. It's not a linear relationship though. Eventually, you'll reach a point where adding more isn't as impactful as it used to be. Okay, let's talk about how big these language models actually are and what that means. LLM come in all different sizes, kind of like cars, a tiny hatchback versus a massive truck. The number of parameters in a model is a good indicator of its size. Bigger models generally perform better on tasks like writing, translation, and even coding. They're more accurate and can handle complex prompts with greater coherence. But here's the catch: larger models are way more expensive to train and run. They need a lot more computing power and memory. You have to find the right balance between how good you want your model to be and how much it costs to actually use it. Okay, let's talk about how these big language models are built. We've got GPT, BERT, and T5, and they all approach language in slightly different ways. GPT is like a really good storyteller. It predicts what comes next in a sentence, making it fantastic for generating text or building chatbots. BERT is more of an expert reader. It looks at the whole context around a word to understand its meaning deeply, which makes it great for things like figuring out if a review is positive or negative. And then there's T5. It's special because it treats everything as a text-to-text problem, so you can use it for translation, summarization, and all sorts of other language tasks using the same architecture. Okay, let's talk about how GPT evolved. We're going to quickly cover the architectural differences between GPT-1, GPT-2, and GPT-3. Think of it like a family tree, each model built on what came before it. GPT-1 was a relatively small starting point with just 75 million parameters. It showed that language models could actually generate text, but it wasn't amazing. GPT-2 took things up a notch with 1.5 billion parameters, letting it produce longer and more coherent pieces of writing. But it still had consistency issues. Then came GPT-3. This one was huge leap. Boasting 175 billion parameters, it was vastly larger than its predecessors. This massive scale led to dramatically improved performance across many different tasks, and the introduction of few-shot learning made it incredibly versatile. Okay, let's talk about GPT-4 and its incredible new multimodal skills. At the heart of it all are transformers. These powerful models really understand how words relate to each other. Then we have LLM, like GPT-4, which are trained on ton of data so they can generate incredibly realistic text. But here's the game changer. GPT-4 isn't just about words anymore. It's now multimodal, meaning it can actually take in information from different types of sources, like images and even videos, alongside your text prompts. It can describe what it sees, answer questions about pictures, and even generate creative visuals based on your descriptions. Pretty wild, right? Okay, let's dive into how Claude's architecture works. It's built on a transformer model, the same foundation as models like GPT, but with some really clever tweaks. The most important thing to know is that Claude uses something called mixture of experts. Think of it like having a team of specialists instead of one giant brain. Each specialist focuses on a particular area, and the system decides which ones to use for each question. It also leverages retrieval augmented generation, allowing it to access and incorporate external knowledge. Basically, it can look things up when needed. And compared to GPT, Claude is designed specifically for conversations, boasting a much larger context window, meaning it can handle incredibly long inputs and maintaining coherence in multi-turn dialogues. Plus, there's a strong focus on safety and reducing potentially harmful outputs. Okay, let's dive into the LLM family. It's been huge in the world of generative AI. Meta released this series of large language models, and what's really interesting is how accessible they are. They come in different sizes, from 7 billion to over 70 billion parameters, which means you can run them on a variety of computers. LLM 1 and 2 were initially focused on research, but then there's Chat LLM, specifically designed for having really good conversations. The biggest impact: the open source release. It's like it lit a fire under the community. Tons of people have taken these models and built upon them, creating even better versions and applications. It dramatically lowered the cost and complexity of working with powerful language models. Okay, let's talk about two really exciting models that came out in 2023, Mistral and Mixtral. Mistral was a game changer because it demonstrated you don't need a massive model to get amazing performance. It's relatively small but incredibly effective. It also had a super generous license, which made it really easy for people to use in their projects. Then, Mixtral took things even further by building on Mistral's mixture of experts architecture, creating a much larger and more efficient model with an incredible context length. Think of it as layers working together. Only the relevant experts get involved for each question, saving tons of computing power. Okay, let's talk about Google's LLM, specifically PaLM and Gemini. PaLM was a huge step forward, really demonstrating the ability of these models to handle complex reasoning and even code. But Gemini is where things get really interesting. It's a multimodal model, meaning it doesn't just understand text, It can also process images, audio, and video. Think about asking it to describe what's happening in a picture or summarizing a song. Gemini comes in 3 different sizes: Ultra for the most demanding tasks, Pro for a good balance of performance and efficiency, and Nano, which is surprisingly powerful enough to run directly on your phone. Essentially, Gemini builds upon LLM's success by taking AI understanding and generation to an entirely new level. Okay, let's talk about Chinchilla. It's a really important model in the LLM world. For a long time, we were just throwing bigger and bigger models at problems, hoping they would magically get better. But researchers found that wasn't always the case. They realized the data itself was often limiting performance. Models were getting too large relative to the amount of truly useful information they actually saw during training. Chinchilla came along and flipped this idea on its head. Instead of just making a bigger model, they focused on using more high-quality data with a smaller model. And guess what? It performed better than much larger models like GPT-3. It really highlighted the importance of efficiently training your models. It's not just about how big they are. Okay, so let's talk about how we can make these massive transformer models actually work without becoming impossibly slow. The problem is that traditional transformers have a really tricky issue. As the sequence gets longer, the amount of computation they need to do grows quadratically. That's a big hurdle for handling huge documents or conversations. Sparse transformers offer an elegant solution. They're all about being smart and only focusing on what really matters. They achieve this through selective attention, meaning instead of looking at every single word in the input, they only pay attention to a carefully chosen group. Think of it like highlighting the key points in a text. There are different ways they do this. Some use fixed patterns based on how words relate to each other locally, while others let the model itself figure out which tokens deserve attention. Another great technique is block sparse attention, where the calculations are divided into smaller blocks. Okay, let's dive into how transformers have evolved beyond the original design. The standard transformer architecture can become really slow when dealing with very long text because of its attention mechanism. It scales quadratically with sequence length. To tackle this, researchers came up with some brilliant variations. Performer uses something called favor, which is a smart way to approximate attention and keeps the calculations linear instead of quadratic. Then there's linformer, which drastically reduces the computational cost by projecting parts of the input into low dimensions. Reformer utilizes LSH, and Nistranformer takes an even more targeted approach, using only a subset of queries. Each of these methods offers a balance between performance gains and maintaining accuracy, enabling larger models to process longer sequences. Okay, let's talk about how attention can sometimes slow down our LLM. You see, the way these models calculate relationships between words, that's through something called attention. It's incredibly powerful, but it has a big drawback. As the text gets longer, this attention process becomes really expensive, growing at a rate of n², which is pretty fast. So, we need ways to make it more efficient. We've got techniques like sparse attention, where we only pay attention to certain parts of the text, and low-rank approximations that shrink the calculations. Flash attention is another clever trick for speed up on modern hardware, and memory-compressed attention helps manage longer sequences, basically a smarter way to remember everything. Okay, let's talk about flash attention, a clever technique that's really boosting how we use transformers. The main problem with traditional attention is that it becomes incredibly slow and uses huge amounts of memory as the sequence length grows. It has this thing called quadratic complexity, which means it gets much slower and needs more space to store data the longer the text you're working with. Flash attention solves this by cleverly rearranging how the calculations happen, splitting things into smaller chunks, fusing operations together, and even recomputing some values when needed, all of which significantly cuts down on memory usage without sacrificing too much speed. Okay, so when we're tackling these really huge language models, training them on a single GPU just isn't feasible. They need massive amounts of processing power. That's where distributed training comes in. Basically, we spread the workload across multiple GPUs. Think of it like a team working together. There are 2 main ways to do this: data parallelism, where each GPU gets a chunk of the data and calculates its own updates, or model parallelism, which splits the actual model itself across different GPU. Okay, let's talk about how we make these giant LLM actually train *. It's a big challenge because they need insane amounts of computing power. So, there are two main strategies: data parallelism and model parallelism. Data parallelism is like having multiple people each read the same chapter of a textbook and then compare their answers to build a single correct version. Each computer has its own copy of the entire model, but it works on different pieces of the training data. It's relatively straightforward, but if your models are really huge, each computer might not have enough memory to hold everything at once. Model parallelism is like splitting the textbook into sections and having different people work on different parts simultaneously. Each device only holds a piece of the model, so you can train much larger models that wouldn't fit on one machine. However, this requires more communication between devices. They have to constantly pass data back and forth as the information flows through these different sections. Let's break down the key differences in this table for clarity. Okay, let's talk about how we make these giant LLM actually work on our computers. Scaling them up is a massive hurdle, and that's where clever parallelization techniques come into play. First up, we have tensor parallelism. It's like taking one huge data block, say a massive matrix in the model, and splitting it across multiple GPU. Each GPU only needs to handle its piece of the puzzle, which drastically reduces the memory pressure on each individual device. Then there's pipeline parallelism, which is kind of like an assembly line for your model. It breaks down the LLM into different layers in this case, and assigns each stage to a separate GPU. Data flows through these stages sequentially, allowing us to process more data at once. The key is that both approaches have their strengths and weaknesses, and often they are combined to get the best performance. Okay, let's dive into distributed training with deep speed. Think of it as a way to break down the massive task of training really big language models like the ones powering chatbots so they can fit on multiple GPU. The core idea is the ZRO, which stands for Zero Redundancy Optimizer. It cleverly slices up the model's parameters, gradients, and optimizes state across several devices, preventing each one from holding a complete copy. This dramatically reduces memory usage. Then there's activation checkpointing, which intelligently trades some computation for more efficient memory management. Basically, it recomputes parts of the calculations as needed, instead of storing everything at once. It's like a clever shortcut. Okay, let's talk about ZRO, Zero Redundancy Optimizer. LLM can be massive asterisk, and that means they need a ton of memory to train. ZRO is a clever technique that helps us overcome this limitation. Basically, it reduces the amount of data duplication across devices during training. There are different levels of ZRO: ZRO-1, ZRO-2, and ZRO-3. ZRO-1 just shards the optimizer's memory, while ZRO-2 adds gradients. And finally, ZRO-3 is the most aggressive. It shaves everything. It's like spreading out a big workload to make it manageable for smaller parts. It's not always a perfect solution, as there can be some communication overhead with ZRO-3, but it really opens up possibilities for training larger and more powerful models. Okay, so we've built these amazing LLM. Now what do we do with them? The key is inference. That's when we actually get the model to generate text. We start with prompt engineering, really thinking about how we phrase our requests to get the best results. Then, there are different decoding methods, ways of telling the model exactly how it should build its response. You've got greedy decoding, which is quick but can be a bit boring. Beam search explores more options for higher quality, and sampling techniques like temperature and top P introduce some randomness to make things more creative. Okay, let's talk about how we actually get text from these large language models. The first method is simply greedy decoding. The model just picks the most probable word at each step, which can lead to some pretty repetitive results. Then there's beam search, which keeps track of several promising sequences simultaneously, giving it a little more flexibility. Top K narrows down the choices to the top K most likely words, and finally, top P or nucleus sampling dynamically adjusts the set of possible words based on their cumulative probability. It's a really clever way to balance exploration and coherence. Okay, let's talk about temperature scaling, a really important knob when you're working with LLM. Basically, it controls how creative or predictable the model will be. Think of it like this: a low temperature makes the model stick to what it thinks is most likely next, resulting in very focused and sometimes repetitive text. It's great for things like code generation where accuracy matters. On the other hand, if you crank up the temperature, let's say around 1.0, you get a lot more randomness and surprising outputs. This can be fantastic for brainstorming or creative writing projects, but it might also lead to some less coherent results. It's all about finding the balance that works best for what you're trying to achieve. Okay, let's talk about how LLM actually create text. It's not magic. They work by breaking down your prompt into smaller pieces called tokens, basically like words or parts of words. Then, the model figures out what the most likely next token is based on everything it's learned. It then picks a token randomly, but more probable tokens are picked more often. And this process repeats over and over, building the text one token at a time. It's like a really smart autocomplete. This slide shows you how that looks visually. Each line represents the probability of picking a different token as the model continues generating its response. Okay, let's talk about how to really get the most out of those powerful large language models. It's not just about asking a question, it's about crafting the perfect prompt. Think of your prompt as instructions for the AI. The clearer and more specific you are, the better the results. We'll cover some essential techniques like giving really clear instructions, assigning a role to the model, imagine it's an expert in the field, and even using few-shot learning, which means providing examples so the LLM understands exactly what you want. Finally, chain of thought prompting can help guide the AI through complex problems step by step. Don't be afraid to experiment and tweak your prompts. That's how you'll discover what works best for you. Okay, let's talk about zero-shot and few-shot prompting, powerful techniques for getting the most out of large language models. Zero-shot means you just give the LLM a task without any specific examples. It's like saying summarize this, and hoping it gets the gist. Few-shot, on the other hand, involves giving the model a few examples of what you want, maybe 2 or 3, showing the input and output format. This helps guide the model and significantly improves its accuracy and consistency. Think of it as providing a template the LLM learns to follow that structure. Experimenting with both is really important to see which approach works best for your specific needs. Okay, let's talk about chain of thought prompting. Large language models are amazing, but they can sometimes get tripped up when tackling really complicated problems that require multiple steps of reasoning. Chain of thought prompting is a clever trick to help them do better. Basically, you show the model to think through a problem by giving it a few examples of step-by-step solutions. You'll provide both the initial question and then break down exactly how to arrive at the answer, like first, we add 1 and 1 together. Then, when you give it a new similar problem, you prompt it with something like let's think step by step, and it will try to follow that same logical structure. It's like teaching the model to reason more effectively, leading to much better results and also making their answers easier to understand. Okay, let's dive into instruction tuning. It's a really important technique for getting the most out of large language models. Basically, instead of just training an LLM to predict what comes next in a sentence, we're teaching it to follow instructions. Think of it like giving clear commands: summarize this article, translate this into Spanish, or even write a haiku about cats. The more diverse the types of instructions you use, the better the model gets at understanding what you want from it. And sometimes we can even take that a step further with techniques like reinforcement learning from human feedback to really dial in how the model behaves based on human preferences. It's all about shaping the model's behavior through targeted prompts. Okay, let's talk about RLHF. It's a really clever way to make LLM actually want to do what we want them to do. Basically, we start by training the model on examples of good responses, supervised fine-tuning. Then we get humans involved. They rank different outputs from the model for the same question or prompt, and this ranking creates a reward model. This model learns what humans consider good output. Finally, we use reinforcement learning to further train the LLM, rewarding it when it produces responses that score highly with our reward model. It's like a constant feedback loop, guiding the model towards better alignment with human preferences, making them more helpful, harmless, and honest. Okay, let's talk about how we're making these powerful language models a bit safer and more reliable. We're moving beyond just training them to give you the best answer. We're focusing on how they give the answer. Two really interesting approaches are constitutional AI and rule-based alignment. Constitutional AI is like giving the model an internal rulebook, a set of principles it uses as its guide when generating text. It's essentially training it to judge its own responses based on these core values. Then we have rule-based alignment, which involves directly defining specific rules and constraints for the model, particularly helpful in situations where you need very clear guidelines, like generating safe medical advice, for example. Both of these techniques are about building trust and predictability into these incredible models. Okay, let's talk about how we make sure our LLM don't go rogue. A really important part of working with these models is understanding something called red teaming and adversarial testing. Basically, red teaming is like hiring a team of ethical hackers to try and break into the system, not in a destructive way, but to find weaknesses before bad actors do. They'll use techniques like prompt injection, where they craft clever prompts designed to trick the model. Adversarial testing takes this a step further. It involves creating specific inputs that are designed to cause problems or lead to undesirable outputs. It's all about finding those vulnerabilities and patching them up so our LLM stays safe and reliable. Okay, let's talk about a really important aspect of generative AI: bias and fairness. These powerful models learn everything they know from the data we give them, and that data isn't always neutral. It can reflect existing biases in our society, which means the AI can unintentionally repeat those same prejudices. We need to look at where these biases come from, whether it's in the data itself, how the model is built, or even just how it interprets information. It's a complex issue, but vital for ensuring that generative AI benefits everyone fairly and doesn't perpetuate harmful stereotypes. Okay, let's talk about a really important challenge when working with large language models: toxicity. LLM are incredibly impressive, but they learn from everything they're fed, and unfortunately, that can include biased and even harmful language. This is a significant problem for several reasons. It can damage a company's reputation, potentially lead to legal issues, and just isn't ethically sound. There are several ways we can try to tackle this. We can use sentiment analysis to get a sense of the overall tone. If something's really negative, that's a red flag. More specifically, toxicity classifiers are models designed to identify offensive or harmful content directly. Rule-based filters, which basically block certain words and phrases, can be helpful for simple cases, but they are often easily tricked. And prompt engineering is crucial. A way you ask the model a question can really influence its response. Finally, it's not enough just to detect toxicity. We need to mitigate it, which means actively working to reduce harmful output. Techniques like reinforcement learning with human feedback help LLM align with what humans consider acceptable, and post-processing filters are applied after the text is generated. And don't forget about red teaming, where you intentionally try to trick the model into producing bad content. This helps us identify vulnerabilities. Okay, let's talk about the ethical side of these amazing LLM. They're trained on lot of data, basically everything available online, and unfortunately, that data reflects existing biases in society. This means LLM can sometimes produce outputs that are unfair or discriminatory. Think about how they might reinforce stereotypes. Also, because they're so good at writing convincingly, they could be used to spread misinformation really effectively. Privacy is another big concern. They could unintentionally reveal personal information. And of course, there's the potential for job losses as these tools automate tasks traditionally done by humans. Finally, it's hard to understand how these models work inside making it difficult to hold anyone accountable when things go wrong. Okay, let's talk about understanding how these massive language models actually think . It's a big challenge because they are often like black boxes. But we can use techniques called model probing, basically asking targeted questions to see what the model is focusing on when it makes decisions. We design specific tasks, like predicting whether something is positive or negative, to check if the model has actually learned something useful or if it's just remembering things from its training data. Then we can look at attention maps, which show us where the model is looking in a sentence. That's super helpful. Or we might try removing parts of the model and seeing how that affects its performance. It's all about peeling back the layers to understand what's going on inside. Okay, let's talk about attention. Generative AI models like transformers use something called attention to figure out which parts of an input are most important. But it can be a bit mysterious how that actually works. So we need ways to see what the model is paying attention to. We have techniques like attention maps, which are basically heat maps showing how strongly the model focuses on different words in a sentence. Then there's attention rollouts, which lets us watch the model's focus as it generates text. Super cool. And finally, researchers use probing tasks where they create specific tests to see what information is being stored within each layer of attention. Okay, so let's dive into how LLM really understand language. It all starts with something called embeddings. Basically, they turn words and even phrases into numbers. Think of it like assigning each word a specific coordinate on a giant map. Words that have similar meanings end up clustered together on the map, king and queen, for instance. These embeddings are created by training models to identify relationships between words based on how often they appear near each other in text. So, if two words frequently show up together, their numerical representations get closer. And the closeness, that distance between those numbers, actually tells us how similar the words mean. We call this semantic similarity. It's a really clever way for LLM to grasp the underlying relationships in language beyond just memorizing patterns. Okay, so LLM are really good at generating text, like writing articles or answering questions. But they are only as smart as the data they've been trained on. That means they don't automatically know about things that happened after their training cutoff date. This is where vector databases come in. They work by converting everything, documents, images, even audio, into numerical vectors, kind of like a secret code. When you ask an LLM a question, it creates its own code too. The database then quickly finds the pieces of information that are most similar to your question, pulling them together for the LLM. It's like giving the LLM extra context and making it way more knowledgeable and accurate. Okay, let's talk about Retrieval Augmented Generation, or RAG. Basically, it's a way to make large language models even smarter by giving them access to outside information they didn't learn during their initial training. Think of LLM like incredibly well-read people who have gaps in their knowledge, things that happened after they were trained. RAG solves this problem. It works in 3 steps. First, it quickly searches a relevant external source for the most useful documents, often using something called a vector database. Then, those documents are added to the prompt before the LLM generates its response. This helps the model stay grounded and avoids making things up, producing hallucinations. RAG is super important because it allows you to build AI applications that are both accurate and up to date, especially when dealing with specialized domains where general knowledge might not be enough. Okay, let's talk about memory. Augmented language models are a really exciting area in AI right now. Basically, LLM like GPT are fantastic at generating text, but they sometimes struggle with things they didn't explicitly learn during training. That's where adding external memory comes in handy. We're essentially giving these models the ability to look things up much like a human would when answering a question. The most popular method is Retrieval Augmented Generation, or RAG, which involves fetching relevant information from an outside source and then using that context to create a response. There are other techniques too, like memory networks and leveraging knowledge graphs. The main advantage? More accurate responses, better contextual understanding, and the ability to adapt to specific needs. It's a game changer for making LLM truly powerful. Okay, let's talk about something really exciting: agents and tool using LLM. Basically, we're moving beyond just having an AI that writes text. Now, these systems can actually do things by combining the power of a large language model with external tools. Think of it like giving your AI assistant access to Google search, a calculator, or even a database, whatever it needs to get the job done. The LLM is the brain, deciding what to do and how to do it, while the tools provide that specific knowledge or capability. It's a really powerful combination. Okay, let's talk about function calling. Think of large language models as really good at talking. They can generate text, translate languages, and even write different kinds of creative content. But often, you want them to actually do something in the real world, like check a weather forecast or book a flight. Function calling is how we do that. It's all about crafting prompts that tell the LLM exactly what tool it should use. Think of it as giving the model a recipe for getting information or performing an action. We define these functions with clear steps and then let the LLM decide when to call them, based on your request. For example, if you ask what's the weather like in London, the LLM might say, I'll use the weather API to get this information. Then it asks you for the location, and finally provides you with the weather report. Okay, so we're moving beyond just words. Multimodal large language models are a huge step up because they can actually see and hear well, not hear exactly, but understand visual information too. These models take in text alongside images or even video, allowing them to answer questions about pictures, generate descriptions for visuals, and sometimes create new content based on what they've seen. Think of it like giving an AI a much richer context to work with, is leading to some really cool advancements in areas like understanding videos and generating entirely new visual content. Okay, let's talk about turning words into pictures. We're looking at text-to-image generation, basically telling a computer what you want to see and it creates an image for you. Tools like DALL-E and Stable Diffusion are leading the charge. The biggest thing here is prompt engineering. You need to be really specific with your descriptions. Think about everything from the overall composition of the scene to the style, and even how things are lit. Stable Diffusion uses a process called diffusion, starting with pure noise and gradually building up an image based on your text. DALL-E takes a slightly different approach, using GAN. It's like a competition between two neural networks working together to produce amazing results. Okay, let's talk about creating sound from words. We've got two exciting areas here: text-to-speech, basically making computers speak like a real person. Modern LLM are taking this to a whole new level of realism. And then there's text-to-audio, which is even cooler. It allows us to generate entire soundscapes and musical pieces just by describing them in text. These technologies use transformers. Think of them as really smart pattern recognizers trained on huge amounts of audio data, allowing them to build incredibly convincing sounds. Okay, let's talk about one of the coolest applications of generative AI, text-to-video generation. Basically, we can now take a written description like a story or a concept and have an AI create a video out of it. It starts with the LLM understanding what you want. Then a separate model predicts each frame of the video one by one. Think of it as building a movie scene shot by shot based on your text. The models behind this are often diffusion models, which are really good at creating images and extending them into moving sequences. While still in its early days, things like realistic movement and complex scenes can be tricky. The potential is absolutely mind-blowing. Resources like Runway ML and Pico Labs are great places to explore this exciting technology. Okay, let's talk about embedding models. They're absolutely vital for how large language models actually get what you're asking them. Essentially, they convert words and sentences into numbers, creating a numerical fingerprint of their meaning. A great example is BERT. Unlike older methods that gave each word just one number, BERT creates contextualized embeddings. This means the the same word can have different numbers depending on how it's used in the sentence. Really clever. We can use these numerical representations to do things like figure out if two sentences are similar or even classify text for sentiment analysis. Okay, let's talk about how we can actually find similar sentences using these AI models. It all starts with sentence embeddings. Basically, we're taking a sentence and turning it into a numerical vector, a list of numbers that represents its meaning. Think of it like giving each sentence a unique coordinate in a giant space where similar meanings are close together. Sentence transformers are specifically designed to do this really well, using technology inspired by those powerful large language models. We use something called cosine similarity to measure how like these vectors are. The smaller the angle between them, the more similar the sentences. It's a really helpful way to quickly find related content. Okay, let's talk about how some of the newest LLM are tackling a really important problem: context. Older models had a limited memory, like they could only read a short paragraph at a time. But now, with models like Claude 2 and Gemini Pro, things are changing dramatically. They've developed clever techniques that let them remember far more of the conversation or document you're feeding them. It's almost like they have a really long-term memory. They use things like recurrent memory mechanisms and sliding window attention to do this, often combined with techniques like RAG, basically pulling in extra information when needed. This means we can get much more coherent responses and handle incredibly complex tasks that were previously out of reach. Okay, let's talk about something really important when working with these massive language models: our memory. They have a limited context window, which is basically how much they can remember at once. It's like having a short-term memory. If you give them too much information in one go, they might start to lose track of what happened earlier in the conversation or document and produce some inconsistent results. Different models have different size windows. Some are smaller, others much larger. But don't worry, there are ways around this. You can break down large chunks into smaller pieces, use something called retrieval augmented generation, where you fetch relevant information from an external source, summarize previous turns, or simply choose a model with a bigger memory capacity. Okay, so let's talk about how we can really make large language models our own. Instead of just using them as is, which they are already pretty amazing at, we can fine-tune them for specific jobs or areas. Think of it like teaching a student. You wouldn't expect them to know everything right off the bat. There are several ways to do this. You can fully update all the model settings, giving you the best results if you have lots of data and want a really customized outcome. However, sometimes we don't have that much data or the resources to train an entire massive model. That's where things like low RA and adapters come in. They only adjust small parts of the model, making it way faster and cheaper. And then there's prompt tuning, which is basically crafting the perfect instructions to get the LLM to do what you want without changing its core knowledge at all. The best approach depends on your specific needs and resources, so it's worth exploring. Okay, so let's talk about how we can make these huge language models actually useful for specific needs. The problem is they're massive. Think billions of parameters. Training them from scratch would be a serious undertaking. That's where PEF comes in. It stands for parameter efficient fine-tuning, and it's basically a set of clever tricks that let us adapt these models to new tasks without having to retrain the entire thing. Though RA is one of the most popular techniques, it's like adding a tiny adjustment layer to the model instead of completely rewriting it. There are other approaches too, like prefix tuning and adapters, all designed to do the same thing, make fine-tuning much more manageable. Okay, let's talk about how we can make these huge LLM actually work on less powerful devices. One really important thing is something called quantization and model compression. Basically, LLM are built with a ton of numbers, lots of them. Quantization is like simplifying those numbers, dropping some precision to use fewer bits per number. Think of it like rounding off decimals. It makes the model smaller and faster. Then we have other techniques like pruning, basically trimming away connections that aren't super important in knowledge distillation, where we train a smaller, quicker model to learn from a bigger one. It's all about making these massive models more manageable and deployable without needing a supercomputer. Okay, let's talk about knowledge distillation, a really smart technique for making large language models more manageable. Basically, we have this huge, powerful teacher model like GPT-3 that knows everything asterisk. But it's slow and expensive to use. Knowledge distillation lets us create a smaller student model that can still perform remarkably well, mimicking the teacher's behavior. The student doesn't just learn the right answers, it learns why those are the right answers by looking at the probabilities the teacher assigns to all possible outcomes, even the wrong ones. This gives the student a much richer understanding. And because the student is smaller, we get faster responses and lower costs without sacrificing too much accuracy. Okay, let's dive into adapters and plug-in tuning. It's a really clever way to boost the abilities of large language models. Basically, LLM are amazing at general knowledge, but sometimes they need specialized skills. Adapters are like little add-ons that you stick inside the model, learning how to handle specific tasks without changing the core LLM itself. Think of them as tiny, focused modules. Plug-in tuning modules work similarly, except they operate independently and communicate with the main LLM through a defined system. It's incredibly efficient because you don't have to retrain the whole thing from scratch. And the best part is that adapters and PTM make it super easy to switch between different skills or adapt to new areas. It's all about modularity and flexibility, which makes them really powerful tools for working with LLM. Okay, let's talk about some really exciting open source LLM. We're focusing on LLMA, Mistral AI, and Falcon 3 models that are shaking up the field. LLMA was initially a research project by Meta, but it's now more widely available and is known for being surprisingly powerful even with relatively smaller sizes. Then we have Mistral AI. They've really gained traction recently because their models are incredibly fast and efficient, often beating larger ones on specific tasks while still delivering great results. And finally there's Falcon, developed by the Technology Innovation Institute. It's a strong performer and comes with a very permissive license, which makes it fantastic for developers and researchers. I've included a simple table to quickly highlight some key differences between them, things like their licenses, parameter sizes, and what they're particularly good at. Keep in mind that performance can shift depending on exactly what you're asking the model to do, so it's always worth experimenting. Okay, let's talk about something really important when diving into open source AI. Licensing. It's not quite as simple as just downloading something and using it however you want. There are a bunch of different licenses out there: Apache 2.0, MIT, and even Creative Commons, each with its own rules about what you can do. The Apache 2.0 and MIT licenses are pretty permissive, letting you use them for commercial purposes as long as you keep the original copyright notices around. But then you have some models that come with stricter non-commercial licenses. And don't forget about dual licensing, where a model might be open source under one license but requires you to pay for a separate commercial license if you want to use it in certain ways. So, always read the fine print and understand exactly what those terms of use mean before you start building your AI applications. Okay, let's talk about how we actually judge these massive language models. What do we use to see if they're really smart? We rely on a bunch of benchmarks, or tests, designed specifically for LLM. MMLU is one of the most popular. It's like a huge general knowledge quiz covering a ton of subjects, and it helps us understand how well these models grasp common sense. Then there's Helm, which is a really thorough test that looks at all sorts of things from basic math to reading comprehension and even whether a model might generate harmful content. And finally, BIG Bench, which is a massive collaborative effort to push the boundaries of what LLM can do with some seriously tricky questions. It's important to remember that these benchmarks aren't flawless, but they give us really valuable data for comparing different models and seeing how well they're improving. Okay, let's talk about how we actually judge whether an LLM is doing a good job. Because these models generate text and don't really understand it like we do, we need ways to measure the output objectively. We use things called evaluation metrics, specifically Blue, Rouge, and Meter. Blue looks at how much the generated text overlaps with a reference text, basically checking for similar phrases. Bruges focuses on whether the model successfully pulled in key information from the reference. And Meta goes a step further by considering synonyms and word stems to get an even more accurate picture of similarity. It's important to know that each metric has strengths and weaknesses, so often we use them together for a really comprehensive assessment. Okay, so when we're looking at how well LLM are doing their job, it's really important to go beyond just a gut feeling. We need some solid methods for evaluating the results. Let's start with 4 core principles. Relevance: does the output actually answer your question? Coherence: is it easy to understand and make sense of? Fluency: does it read naturally like something a person would write? And finally, accuracy or factuality is vital. Is all the information correct? To get really good results, we should use multiple people to judge each output, blind them to which model created what, and ideally use tools to help us keep track of our ratings. Okay, so generative AI isn't just about cool demos. It's actually being used everywhere right now. Let's look at some key areas where it's having a real impact. First up, marketing LLM are helping companies churn out blog posts, social media content, and even personalized emails faster than ever before. Then there's coding. Tools like GitHub Copilot are seriously changing how developers work by suggesting code and even writing entire functions based on what you type. We're also seeing huge advancements in healthcare, where AI is being used to predict drug interactions and design new medications. And of course, chatbots, the more advanced ones powered by LLM, are becoming incredibly effective at handling customer service requests. It's genuinely a game changer across multiple industries. Okay, let's talk about what's coming up. The future of generative AI is incredibly dynamic. We're seeing a huge push towards multimodal models that can handle all sorts of inputs: text, images, audio, video, basically anything. Imagine an AI that not only writes a story, but also creates a visual representation to go with it. Personalized LLM are another big trend. We'll move away from generic models and create specialized versions for specific users or professions. Think about an AI assistant perfectly tailored to your needs. Edge AI is key too, bringing this technology out of the cloud and onto devices like smartphones and wearables. And importantly, as these models get more powerful, understand the why they generate what they do. That's becoming increasingly critical through research into explainable generative AI. Finally, we are continuing to improve how well LLM align with human values. Thank you for watching.